Ediacaran fossils are a bag full of mysteries wrapped up in problems. The bizarre Dickinsonia is one of the best known, and one of the most enigmatic in some ways. There are intriguing hints that this thing was actually at least closely related to animals, maybe in the stem group, maybe even higher up. One of those features is that it appears to have been able to move. But how? Let's look at the evidence for that and see what we can make sense of it, irrespective of what sort of organism it actually was. The Cambrian Explosion was when we had the appearance in the fossil record of many different groups of animals that we can definitely recognise as animals. This happened relatively quickly, around the very latest Ediacaran into the earliest part of the Cambrian, and before that we have the Ediacaran. This has its own biota of fossils which are extraordinary, richly preserved, diverse, abundant in some places, but still enigmatic. There is currently a prevailing school of thought that many of these can be kind of squeezed into early animal evolution, whether that's within the base of the tree of the animal groups that we know today, or somewhat further back, maybe in the stem group leading to the first groups that are now recognisable. And this is still debatable because no matter how many arguments one puts together, it's still difficult to take something like that and see how that fits in relation to things like cnidarians, sponges, jellyfish, the more familiar groups of animals. It's very difficult to interpret these flat carpet-like things with sort of pseudo-bilateral symmetry and very fine transverse ridges going across them with the things that we know and love today from the seaside. And it is a bit of a dichotomy between the Cambrian faunas, when almost everything is at least vaguely familiar, and the Ediacaran ones where they're not. So Dickinsonia, the one I'll be focusing on today, has a huge literature of people trying to puzzle it out, looking at all sorts of aspects of it. I am not a specialist in the Ediacaran. I tend to work on slightly younger rocks where we mostly know which major groups we're looking at. But it is still an absolutely fascinating time for me. And because I'm not directly involved with the debate, I feel that I can step back a little bit and present a slightly unbiased view in that sense. It may not be the most popular view. Other views are available as well. But I can still make some sort of assessment, which hopefully you'll find interesting along with my reasoning for why. But Dickinsonia itself is too big of a problem to tackle in one go. There are so many aspects to trying to understand it that I'm not going to go for all of them. It's just too big. What I will have a look at today, though, is the evidence for how this thing moved. Whether it moved, what it was doing, and what mechanism there was for that. Irrespective of what sort of animal or non-animal this could have been, but trying to understand that on functional grounds based on the fossils, on their preservation, and on basic reasoning. So we're going to be looking into some interesting ideas, see what has been discussed already, because there's a lot there, and go from there, see if we can reach any sort of conclusion, at least on the likely possibilities. Because it's a really fascinating area when it clearly didn't have legs. So what did it have? I'm going to be drawing on quite a few papers when I'm doing this video, especially one by Evans et al. In 2019, which is a really nicely balanced summary of the evidence up to that point and counter evidence for previous arguments as well. So it's a nice starting point. Let's start with the basics of what these things were, though. So this is a cast. It's an accurate replica of one of these fossils. It's not a model or anything like that. But there are quite a large number of these and their relatives found across many of the White Sea assemblage time. So this is from about 560 to 550 million years in Russia and Australia especially. And there's not just Dickinsonia, there are relatives such as Yorgia and there's some others as well, which are rather similar. There can be different shapes, and in some cases, like Yorgia, there is a sort of a region at one end that could be interpreted as sort of a bit like a head, although there's a sort of asymmetric sort of crook in the middle of it. So it's a peculiar thing. But they are all flat. They are sheet-like structures, mostly either sort of subcircular to elongated, and they can get up to 80 centimeters long. So they are quite large. But in terms of thickness, it's minimal. Now, the basic structure is that it has this sort of groove down the midline, and coming off that, there are very fine transverse, sometimes oblique, but sometimes strictly transverse, other ridges, grooves going off on either side. The upper and lower surfaces appear not to be really distinguishable. There doesn't seem to have been a differentiation between the two. In terms of internal structures, we don't really have any evidence for that. What we've got is a preservation in the sandstone deposits of the Ediacara biotas, which are difficult to interpret at the best of times. The preservation style of these things is really hard to get your heads around, and I'm not entirely sure that we yet have a perfectly good explanation of it. It seems to be related to masking by microbial mats growing over the surface of them and then collapsing and producing a negative impression on the bottom of beds. It's a bit weird. But they are very strange looking fossils. They don't closely resemble any of the early animals in terms of, well, to be honest, they don't resemble at all any of the early animals, apart from possibly the placozoans, which are today an extremely small group of highly miniaturized things which have a body consisting of a sheet of cells, no real symmetry. And there's a recent paper which actually shows that when they die, they basically disintegrate into individual cells very, very quickly, sort of minutes to hours, and therefore have virtually no chance of ever fossilizing. In contrast, one thing we can say about things like Dickinsonia is that they were fairly tough, because there are specimens that are folded. There are ones which are torn, which still leave impressions in the microbial mats that they were living amongst. We don't see small fragments of them ripped up everywhere. We just get very occasionally one large one has been torn in half. So they were not things like the mats themselves, which were easily ripped up by waves and torn into little fragments. This is a relatively robust organism. It also has much more complex structure than placozoans, for example, but there's one feature that does seem to be similar, which is that as far as we can tell, Dickinsonia and its relatives had no gut. There's no structure that looks like a gut inside them, and they are believed to have fed by direct absorption of nutrients over the surfaces, possibly through cilia, possibly through some other mechanism, but they are thought to have digested from the external environment rather than having a mouth and putting things inside them first. That's really interesting, and it's relevant when we're thinking about how and if they could move, as to why that would work and what sort of physiology they might have had to support any sort of processes like this. I know I'm hedging this in all sorts of very loose language because this is what we've got. Unless we start making assumptions and saying, well, it's an animal, therefore it had muscles, therefore, I'm not going to do that. I'm going to be looking at things as we actually know them and trying to work from the evidence there and try to keep assumptions out of it, because I like doing it that way. It tends to be more reliable, I find. That said, as I mentioned, there are some lines of evidence that really do point towards animals, at least potentially. So on the first one, we have sterols. people have actually looked for chemical fossils, biomarkers, within fossils from the White Sea Formation of Russia. And this is a paper by Bovitsky et al. In 2019, where they found quite a large number of sterols that indicate the breakdown of significant quantities of cholesterol. This is interesting because today, although cholesterol is fairly widespread among eukaryotes, only animals have large amounts of it. So this was an indication that it was at least closer to animals than to living animals than it was to their next nearest relatives, which are single-celled things like choanoflagellates. So that's definitely an indication that it's somewhere towards or possibly within the modern animal groups. Then there is growth patterns. So Huxima et al. Were studying the growth dynamics and the patterns of insertion of new segments as these things grew, and found that there was a subterminal addition of segments, sections. Segments is too loaded a word, but these transverse sections, and then a sort of inflationary phase. And this is, again, a feature that is pretty typical of animals. And that's not to say that you can't have that happening with any other group, but again, it's supporting them being within the animals, or close to them at least. And they also assume, based on that and various other considerations, that they thought it was within the crown group of animals, and actually within Eumetazoa plus Placozoa, which I think is also now Eumetazoa, depending on your phylogeny. But so not even the earliest animals, but somewhere actually up into the tree. That was based on some things that may be less reliable, though, so we'll stick with they've got this growth pattern. Then we have the symmetry. Here we have what is approximately bilateral symmetry. However, in at least quite a few cases, it's not strictly bilateral, but is glide bilateral. Each side is offset from the other. You add to that things like Yorgia, the end section is clearly asymmetric. It's clearly going off to one side. So it's not strictly bilateral in these groups. It's sort of glide bilaterally symmetric, which is a feature that you do get within bilaterian animals in a few places. You can see it in lepidocolian macrovidians, for example, and even to some extent in vertebrates. Some of the arrangement of the muscles and so on, the structures within vertebrates, can be seen as glide symmetric. So there is flexibility within bilateral symmetry and glide symmetric symmetry, but there's also the evidence that bilateral symmetry is not restricted to bilaterians, but may be ancestral for cnidarians and possibly for animals as a whole. There's a lot of uncertainty over the deep origins of symmetries and exactly where true glide symmetric symmetry would fit within this. So a lot of these things are not easy to pin down the significance of. And then the other feature they have, which has been considered to be a feature of animals, is mobility. That is something we will come back to for the rest of the video. So mostly this assignment to Eumetazoa in particular, or to Bilateria, is based on similarities to extant groups. But it tends to put a lot of weight on particular features and ignore quite a lot of major differences, in my view. And especially, it doesn't consider the possibility, in some cases, of an extinct group which shares some of these basic features that are being compared, like the sort of pseudo-bilateral symmetry, but doesn't consider the possibility of them being secondarily involved convergently or have some sort of deep sharing of genetics, going back to organisms that branched off before any of the living animals. So I'm not going into that discussion of exactly where Dickinsonia is. I'm not saying it's not to do with the bilaterians. I'm just going to leave it there. We don't know for certain, we need more evidence, and for that we need to study how it actually lived and how these things worked. So where is the evidence that these things moved? In short, it comes down to apparent trace fossils. So usually you get a Dickinsonia or one of its relatives as an isolated individual fossil on a bedding plane, but sometimes it's not alone. Sometimes you see them as lines of them or clusters of them, which seem to be impressions of the same organism. In many cases, there's a gradation. So from the one at one end, you get a really sharp impression of the organism itself. And then at the other end of this sort of chain of these impressions, you have something which is much fainter. It's not always the case, but quite often there is a gradation in the clarity of the fossil. There is also, in some cases, little sort of scratch marks. These are very rare, I believe, but sort of indications of something having dragged slightly over the surface between two of these impressions, or at least leading up to one of the isolated ones. Now, it has been suggested that the poorly preserved ones are simply decayed examples of very similar individuals, but it doesn't make sense of there being a chain of them, evenly spaced and usually evenly oriented, which seems to show the impression of the same actual individual. And so there seems to be pretty good evidence that these things could actually move. They could leave an impression in the mat in one place, move along a little bit, normally slightly more than their own body length, and leave another impression, and then move on again and again and again. And that, the more you think about it, is really, really strange. It's not always the case that you see this, and there has been work studying the distribution patterns of Ediacaran fossils on large bedding planes, and what you find is that the Dickinsoniids seem to be effectively random in their distributions. That this is different from even, and it's different from clustered. Random is there is no pattern. And so you do not get chains of them, usually. So this does seem to be a genuine feature. But what is it actually telling us? What are we seeing here? Because even that isn't actually obvious. These apparent trace fossils are really finely detailed in some cases. They are very clear, they're sharp-edged, they don't show any smearing or anything like that. They are just impressions in the algal mats, which remember covered all these surfaces, which seem to have been sort of impressed into it or possibly etched into it. It's difficult to be certain. So if we go back to this idea that it has no gut and appears to have fed through the surface, over the entire surface, then maybe what we're seeing with these impressions is the actual evidence for digestion. These organisms were emplaced one way or another onto the surface of the mat. They spent some time there actually digesting the mat until they moved on again and left an impression behind them of where they'd been digesting it. And that is probably the most widespread idea of what these impressions mean, I believe. And in some cases, there is such fine detail in some of these impressions that we see in some of the work by Ivantsov that there appear to be sort of fan-like arrays of tiny structures, filament between these ridges, on the transverse ridges going across it, which may be evidence for cilia on the subsurface, that these things were actually digesting the surface with cilia. However, that's not the only possible interpretation, and it's important to remember as well that these microbial mats are not hard structures. We're not looking at solid bound masses of resin or something like that. These are very light, fluffy consortia of microorganisms. We know what they're like because we see them all over the place today. You look in any sort of puddle that's drying out in a field somewhere, and you'll get biofilms growing over the surface, which are ploughed through by any passing snails. They're very soft, delicate structures, and it's all waterlogged, of course. This is all underwater. It's not as if they've hardened and dried out. And McElroy et al. In 2009 did some experiments in laboratories based on the impressions that could be created by things like seaweed on microbial mats. And what they found is that you can have simple passive movement of a bit of seaweed onto the surface of the mat, which can create a whole series of impressions in the surface of the mat simply by the weight of them pressing down onto the surface. And it's what you might expect when you think about it, when you have experience of these mats, then you would expect just the resting of any relatively soft organism, but tougher than the mat itself, on the surface would leave an impression. So is it actually any evidence of digestion going on there, or is it simply the impression of where it rested? Now, McElroy et al. Expanded this to suggest that you could get this by a simple oscillatory movement. So wave action, for example, during a tidal sequence, could lift up one of these Dickinsoniids, drop them in one place, pick them up again, drop them a bit further on, and so on and so on. And that was a pretty compelling argument at first glance, but this is something that the Evans et al. Paper actually addresses and seems to be showing that there is indeed evidence that these things were more directed than that. Part of that evidence is that you can look for evidence of current activity, movement of sediment particles within the beds that you're looking at, and plot the distribution of the angles, the orientations of these structures. And they find that there are clear preferred orientations in the sedimentary structures, but the chains of Dickinsonia are effectively random. They're going off across all sorts of different angles. That could be something much more related to the environmental conditions changing from between one moment and another, and those impressions build up over a longer time than the sedimentary deposition. That could be explained that way. But they also show that there is directionality in the orientation of the fossils themselves. So the anterior seems to be at the front of this organism which is moving sequentially. And whichever direction the chain is in, the same end of the organism is pointing forwards. And that does seem to suggest some degree of control, whether passive or active, on the movement process. We'll come back to that. So I think pretty much everyone is happy that these things were moving in some sort of a predictable, if not deliberate, way. The obvious thing to look at first is standard movement processes of animals. If this is interpreted as a bilaterian worm, which you often see that phrase in the literature, then you have a structure which would move through muscles. Now, there is some evidence of deformability in Dickinsonia that has been interpreted as evidence for muscles. This includes the impressions of the organism extending out beyond the margins of it in some fossils, implying that it is contracted a bit. Now, there are various ways that things can contract. I mean, they can lose water, or it's all sorts of things. But one possibility is through muscles. And if it's actually contractile, and that is relating to muscles, then that would fit with it having sort of concentric muscles, possibly longitudinal, possibly radial. So along those transverse structures, the ribs that come out from the side. And then it would be able to move in a peristaltic motion by sequentially pulling the muscles inwards, contracting and expanding them along the body, and that would give it a push forwards. So that has been suggested, and even the asymmetry of some specimens where it's much more advanced on one side than the other, it looks like it's been sort of pulled in on one side. Now, either those specimens were deformed individuals, or it was something which was quite strikingly contractile. And if it was contractile one side then the other, then you end up with a situation of possibly moving like that. But if it was moving in any sort of way of that nature, how on earth is it not leaving a massive great motorway behind it? We've already established that algal mats, bacterial mats, are soft. We can see in all these trace fossils that occur in places like Ediacara, White Sea, where you get these fossils, there are these tiny little trails on the surface, helminthoidic nites and things like that, where you have a furrow sort of bored through the surface of this mat with the debris pushed to the side. And that is by something tiny, usually less than a centimetre. Sometimes a millimetre long thing is leaving these really obvious trails in the mats. We don't know quite what made them, possibly amoebae, possibly small animals of some sort. We just don't have any evidence for that at the moment. But whatever it was benthic, it was on the surface, and it completely destroyed the mat. You can't have something like that, even centimetre size or smaller, moving through that surface, apparently, and not leaving a trace. And an obvious trace. And yet, between these impressions of Dickinsonia and the next one, there's nothing. Almost nothing. In a couple of examples at least, there are very faint little sort of scratches near the centre. Not the outlines of the whole thing, but just a few little ridges sort of meandering over the surface, which look like there might be a slight indentation of something that barely brushed the surface. Peristaltic worm motion? That's just not going to work. And I think we can rule that out on that basis. There would be huge great furrows if you had basically a tough mat-like thing peristaltically moving over the surface by contracting muscles. You're going to see it. So I don't see there's any chance of that at all. Okay. Next option, which is also very widely believed as possible, I think, is ciliary movement. So you have a thin sheet which is covered on its underside and probably the upper side as well by cilia. And these are what it's using to feed, to digest the mat that it's going over, and also, potentially, to move. Now, cilia are very, very delicate structures. They're also tiny, and it's a question of, firstly, whether cilia could move something on that scale, something which is robust enough to be able to be torn and leave quite chunky fossils behind. And that, I think, is dubious. I mean, you could find some way of having an extremely light, maybe neutrally buoyant, or maybe even slightly positively buoyant structure which would lift up off the surface given half a chance, and is held down by thousands or millions of cilia that are just sort of clinging to bits of the mat. You could have something like that going across it. But then we do know of one other animal today that moves by means of cilia, and that is placozoans. Now, these have recently been studied, and in this same paper where they described the fossilization potential of these things being virtually zero, because they are so much more delicate than the Ediacarans were, they also look at any evidence that could be left behind in other ways, namely by trace fossils. And they found some. It seems that placozoans actually leave quite recognizable trace fossils in sticky mud. So, again, to have no trace of this moving seems extraordinary. The only way you could really justify that would be to say that the impression that is left in this mat, the trace fossil, is not anything as simple as the impression of a solid weight pressing down on it, but is much more an active digestion effect, that you have destruction of the mat by the organism for quite a long time, and that any light pressure wouldn't really have any effect on it at all. That also doesn't seem to be viable because of, again, the trace fossils that we do have. We have things like scratch circles where bits of seaweed are stuck in the mat and are being washed around, and they create quite clear marks on the surface of the mat. So even something as light as a little bit of seaweed that hasn't been fossilized is leaving really obvious traces in these surfaces. So again, I don't think that ciliary movement can make sense of this. It can't allow for there being no trace at all of this organism moving from one place to another over the surface. So what else is there? Well, one option that has been suggested, which still has muscles involved, is active swimming. That this thing was basically a magic carpet and sort of swum by waves going along it like various sort of worms and even fish do today. Flatfish, I'm thinking. And then, so this would have to lift off the seafloor suddenly without damaging the impression, and then sort of flap itself along, flop down onto the seafloor again next to it. Now that's difficult to prove, basically, and you have something like powered liftoff, but the only problem is that it never seems to damage the impressions on the mat. So in the traces, we see these perfect impressions. And as far as I'm aware, there's never been one found in which the edges are smeared by this thing actually lifting off. And if it was being pushed off by some sort of muscle movement, then you would expect those impressions to be damaged in some way. But then also, again, if it was powerful enough to be able to lift itself off the surface, move some distance and then drop down again, why is there so much consistency in the small distance, these tiny little hops that they make, just slightly longer than their body length? If they're going up into the water and there's any sort of current, why don't they get sort of washed off course, or why don't they go further sometimes and less far another time? If it was purely powered and not at the mercy of currents, for example, it's difficult to see why the exact motion was so consistent. And apparently the distance that they moved between these traces is proportional to the size of the organism. So it's always a little bit more than one body length, and the larger ones move proportionately further. But relative to the body size, it's always the same length. And that I find very hard to understand from any sort of behavioural perspective. So my problems with this are really that the movement we see is too regular and too independent of the ambient conditions. If these are going across the current or through the current or against it, and usually it's in the same linear arrangement with the same distance between impressions, it's very difficult to understand how that would really be happening. So because of all these issues I have with the current explanations, I've been wondering if there's some way of making it more non-biological. So it's constrained by the organism, but there is a physical process by which it ends up moving. And possibly there is, I'm not totally sure of this, but just throwing this out there to you lot, because I might as well. I'm probably not going to be publishing on this sort of thing at all, so just ideas to think about. But we have a sort of carpet-like animal, organism, living on this sort of microbial mat, which is a little bit sticky, and it's staying there for some time to leave a decent impression. And it's in a relatively turbulent, shallow water environment. There would be waves, there would be current action, and so on. Now, if at a certain point in its feeding cycle, for want of a better term, if it dissolves or digests the mat for a little while, then one corner, and always the same end, starts to lift up off the surface, for example, then that could potentially catch the current. So water movement going from this direction would do nothing. Water movement going that way would actually peel it back and raise, because of pressure on the underside, the entire mat off the surface and push it along. So you imagine you have a mat like that, and it is pushed up and sort of flumps down again. So you can imagine this being a mechanism where it briefly lifts off, gets lifted by a current, and then, because of the hydrodynamics of a flexible mat, just ends up flopping onto the sea floor a short distance further on. Now that distance is going to be dictated by the surface area that is being picked up by the current. And so the larger ones would go slightly further. It would only happen after the current has reached a certain threshold. If it's too slow, nothing would happen. If it's too fast, probably it wouldn't be lifting up in the first place. So you could have a situation where in still conditions, after feeding for a while, the edge of it lifts up at the what is described as the posterior. That, with the right conditions of water flow, lifts it up and deposits it in the same direction a certain distance further on, which will be consistent because it's dictated by when that current hits that threshold of flow speed at the time that the thing is lifting up a corner. It's totally speculative, obviously, but I'm trying to come up with a way in which you could have a situation for this to move without any disturbance of the impression that's left behind. In this case, there's no muscular activity. There's no distortion of the initial impression. There's simply a peeling off and lifting up by the current and then dropping it a short distance downflow. So in that case, you've got something which is a biologically controlled movement, but is not actually active movement. It's passive, but it's initiated by a certain sort of curling of the edge of the organism. It's very difficult to find any way of explaining all of the observed features that we see in these fossils. It is completely science fiction in this case. I don't think I've got any way of finding direct evidence that that is what happened. I don't think that's necessarily possible. But at least it doesn't have the glaring contradictions that we see with something like muscular peristaltic movement through a microbial mat, or even the takeoff with active swimming by mussels. That should leave quite characteristic smears depending on where the muscles actually worked and where the liftoff happened. This doesn't look anything like that. It looks like it's literally just peeling off the surface with no pressure at any point and then being dropped shortly afterwards. So hopefully this sort of scenario I've just come up with is a way of doing that mechanistically, semi-mechanistically. So you have a very simple process that could be related to a simple element of biology, folds up at one corner, takes off, falls down again. Under the right conditions. Now, I've not done any fluid mechanics on this or anything like that, so I'm not saying that I think this is the answer. I'm throwing out ideas to see what might actually work as an explanation of the traces that we get left behind after this type of movement, and which doesn't contradict things that we already know. So just go with it for a minute. So in that case, if we say that, okay, this is a possible explanation for it. So nothing today really shows the same pattern that I'm aware of. It's a big world, I might have missed something, but I don't know of anything else that uses the ambient water to do a sort of flollop and drop down a little bit further on. it would require a certain degree of movement, so the ability to curl at one side. But of course, that doesn't mean muscles. There's no evidence for muscles, no direct evidence. There's evidence for contraction, and there's evidence for being able to flex. So we know it was flexible, and if this was the mechanism, then it could flex itself up from the surface, but that could be an automated environmental response, that once it's fully sort of satiated in its feeding mode, then it just leads to a gradual curl at the end through differentiation of cell contents, whatever. There are all sorts of ways in which you can do that. I mean, sponges can move and contract without any muscles because they use sort of collagen fibrils and so on to do a similar sort of job. So there's all sorts of ways of doing it. It doesn't imply muscles. And we have no evidence yet of muscles or nervous systems in any of these fossils because nobody's yet, as far as I know, found Dickinsonia in a Burgess Shale type preservation in a mudstone. Maybe that would help us, or maybe we'd still see no detail on the internal structure. So none of this answers that question of where on earth Dickinsonia fits into the history of animal evolution or its precursors. But if it's helping us to recreate these organisms in our imagination, putting together some image that might actually work for how these things function, then that's got to be a help. Because too often, I think a lot of these very early strange things that have very little, obviously, in common with Cambrian organisms are sort of squeezed into the wrong sort of place. So the idea of Dickinsonia as a peristaltically moving worm just doesn't match what we see in the trace fossils. So that is not a viable explanation to me. It's not a viable interpretation. This, whatever this was, it was doing something quite different to what a worm does. So it's a weird and crazy thing, Dickinsonia. And I wish I knew exactly what it was in some ways. On the other hand, it's really nice to have a mystery. But there are so many mysteries in this Ediacaran biota. So Dickinsonia is one of the archetypal ones. It's one of the ones that's best studied and has the best evidence for being at least close to animals. But when you reconstruct it, as I've done there, in terms of how it was living, how it moved, it's very easy to start dissociating this from living crown group animals entirely. If we get more evidence that points to it being related to Neisarians, or indeed that confirms some sort of Placozoan relationship, then brilliant. I'll be looking forward to it. But at the moment, I don't think that evidence is there. An association with animals, more than likely. Stem group animal, I would say, based on morphology, is far more likely than crown group, but who knows? I don't have an answer to that one, and I'm not pretending to. But what we can do is look at the evidence we have. And when you look at how this thing moved, well, there's plenty of weirdness there for everyone. So let me know what your thoughts are on this. Can you come up with other ways that this could move in order to explain this pattern of traces that it leaves behind? Because I can't. I'd love to see your thoughts, see what your comments are, and yeah, I'll see you again soon. Bye for now.